This begins our notes on 1.8, and you probably remember from pre-calculus that we graphed several functions like this. It might take you down memory lane about how we did rules like exponents are the same, you divide the leading coefficients, and just be thinking about what that even means right now. I'll re-explain that here shortly. Same thing with this. Here's a graph of this function. Think about why there's a slant asymptote in this problem. Definitely think about how we got vertical asymptotes, which actually brings me to the difference between infinite limits and limits at infinity. The subtle difference is one is talking about vertical asymptotes. That's what the infinite limits here, where limits at infinity is asking for the end behavior of those two. Now, if you misconstrue them, as long as you write the correct math lingo, then you'll be fine. So, for instance, it's basically saying that we have an a value, either on the left or the right, of some function, and we're asking what the is the answer infinity or negative infinity. So that's an example. And the example of limits at infinity are basically saying, what about if the limit as x approaches infinity of some function? And we could still have infinity as an answer if it's a slant asymptote like in this one, or a numerical value. So that's just kind of the subtle difference. And let's actually do this. So this one's labeled f, this one's labeled g. So if I were to ask you the limit as x approaches 2 on the left side of f of x, well, since it's the left side, it's going infinitely down. And then just switching one thing about this, if we were to change it to limit as x approaches 2 on the right side of f of x, it's going infinitely up. I guess I have all these answers down here. I guess I didn't even realize I was just rewriting myself. And then if we look at g of x, -1 on the left side is going infinitely down, so negative infinity, and -1 on the right is going infinitely up. Now, for the record, because I've mentioned it before, I might as well mention again, all of these answers are does not exist, versus as we look at the next one, there are a few that actually does not exist. As we look at the right and left end behavior of each of these. Now, because f of x has a horizontal asymptote, we're looking at that horizontal asymptote. So going to infinity is the right side. We're going closer and closer to y equals 2. And the same thing is on the left. Negative infinity is infinitely to the left. It's still positive 2, but it's on the left side. Now, this is what I'm talking about, is you can still have positive infinity because this is going up with no end in sight. It's getting closer and closer to this asymptote, but as far as a y value, it continues to rise. So this is what I mean, is you can still have infinite limits, and this is sort of your clue that these two have slant asymptotes, if you remember from pre-calc. Moving forward to the next page, you do need to make sure you remember the end behavior for polynomials. And again, just think back to Algebra 2, pre-calc, and things like that, where this is very nicely laid out. We have a negative leading coefficient with an odd degree. This is why we make you learn this more than 1 year before this. So the negative leading coefficient means it's flipped, and the odd degree, this function looks something like this. And because it's asking for the infinite, that is the right end behavior, well, what's the function doing? It's going infinitely down. So this answer, let me change colors to kind of liven up what the answer is negative infinity. Or again, you can write down does not exist. So where does this get a little bit confusing, and I don't even think it's that confusing, is what about when you have the answer in factored form? Okay, well, what happens if you take a negative value and you were to square this out? Well, a negative times a negative is going to give you a positive. So what it boils down to is this is going to be x squared times x times x. So eventually what I'm getting at is that leading coefficient will be a positive x to the fourth. And I really don't care about anything else. We have a positive leading coefficient, and now it's an even degree. So there's some bumps if you were to try and graph this, possibly. And we're looking at the negative side, so as it goes infinitely to the left, the function is going infinitely up. Let me go back to that purple color. So this answer would be going infinitely up, or does not exist. But I want you to practice this behavior that we've talked about. So the idea that I was alluding to before with this rational function and this infinite behavior, this is basically saying as x gets moves further and further to the right. So if we were to try and graph this function, what goes left and right, basically what this question is asking for are your horizontal asymptotes. Well, if you remember from pre-calculus, we learned this goofy thing of Bobo Botno eats DC. Where we're looking at the exponents are the same. We're looking at the degree in the numerator and the denominator, and then we talked about how you divide your leading coefficients. So as I look at this, the leading coefficients in this problem would be -2, because that's the coefficient attached with the highest exponent, over 1. And it's kind of set up nicely that we're looking for the y value of the horizontal asymptote to help explain why this answer is -2. Now I'm going to get into more of a calculus explanation because these other things, if it's bigger on bottom, then the horizontal asymptote is 0. Okay, but you might get confused on how to get this if it's bigger on top, because you never write the limit is no, there's none. It's either going to be infinity or negative infinity, or you can write does not exist. But be ready for a multiple choice where that's not an option. So what I like about this is this guy sets this up as it doesn't matter what the numerator is as long as it's a constant. And then you have x in the denominator. Because if you were to graph these functions, as long as it's a constant, you're going to get a function that looks, sort of like this. If it was just 1 over x, it would look something like that, or, it might even be really, really skinny and then shoots down, things like that. But what you notice is if we talked about the infinite limits, whether we're looking at this function where it's 1 over x, or 3 over x, or 1 over x squared, all of these problems limit as x goes to infinity or negative infinity. This is kind of poor notation. We don't typically do this, but I'm just doing this for time, and as I stumble through the words, I'm not actually saving any time. Like I said, as long as you have a constant over x to some power, because the only thing that's different is when you square, you get positive numbers. But whether you're going to positive infinity or negative infinity, you're going to get closer and closer to 0. And that actually helps explain our horizontal asymptote problems, because we learned the premise of, and you can read this in your notes, we learned the premise in this problem of Bobo, right? Bigger on bottom, so this answer should be 0. Okay, that was the pre-calculus way of figuring this answer out. And by the way, you have to make sure that it's an infinite limit, like we're going to infinity. The actual way of figuring this out, though, is what they do, the math people that created this, is they divided everything by the degree in the denominator. So I'm going to do x divided by x squared. I'm talking about this piece. Maybe I should highlight. I got it from this piece. Plus 2 over x squared over x squared over x squared. I hope all of you are sitting there and thinking that this is okay to do as long as you divide everything by the same thing. It's okay. So we can clean this up a little bit. And we can say, okay, well, x over x squared, that's 1 over x. Can't really clean that up, 2 over x squared. X squared over x squared is 1. 5x over x squared is 5 over x. And you can't really change this. But now what we can do is we can do each individual limit. Well, the limit of, as x goes to infinity, of 1 over x is 0. This, 0. This, 1. This, 0. This, 0. From the rules we just established. So what we're left with is 0 over 1. Well, what's 0 divided by 1? 0. And that's actually where the rule comes from. And that rule still applies as we go to the next one, where you learn in pre-calculus this kind of goofy thing that eats DC. Again, you're doing horizontal asymptotes when it says the limit of x goes to infinity. So this answer should be 2. Well, let's actually do calculus now, where you divide every piece by, I guess I should have stuck with my red color, by x squared. By the way, I'm looking at the denominator. I didn't get that from the numerator. It's always the denominator. 7x over x squared plus 6 over x squared all over x squared over x squared. You can see why, if this is a multiple choice question, you probably wouldn't do all this work. Let me just clean it up, because the x squareds will cancel, so we're left with 2 plus 7 over x plus 6 over x squared all over 1 plus 5 over x plus 6 over x squared. And now we can do each individual limit where this is 0, this is 0, this is 0, this is 0, and we're left with 2 divided by 1, which is this value. Pretty nice, huh? So what happens when we throw in where the bigger on top? Now, I think you can tell by looking at the graph. It's definitely, we just learned no horizontal asymptote. We did practice slant asymptotes. So if you go back to pre-calc, you might remember. But now we want to state the behavior as we go infinitely up. So now I want you to get used to writing infinity. And that's why it's nice to divide by the denominator's coefficient. So as I go back to red and divide everything by x, so we have x squared over x plus 3x over x plus 2 over x over x minus 1 over x. Let me just simplify it right there so I don't have to rewrite it. That one of these x's will cancel, this will cancel, this will be 0, this will be 0. Now when you do direct substitution, let me do an arrow real quick. It's actually fine if you leave it as an equal sign. You have infinity plus 3. Well, I don't know how much work you've done with infinity, but if you add 3 to infinity, you just get it's actually the same size infinity. But this actually shows why the behavior looks like that. So I'm going to pause the video here, or stop it, and make another one to finish up these notes.